So welcome everybody to this afternoon parallel session. It's a pleasure to introduce the first speaker, who is Mariam Pirashvili, and we talk about on the center of cross models of groups.
Thank you. Thank you for the introduction, and thank you for letting us speak here. So yes, I'm going to talk about a new definition of the center of cross-models of groups. So there exists another definition from the 80s, from the 1980s, and I will mention it towards the end of the talk a little bit and draw some comparisons and try to justify why I think mine is better, at least one interesting in different ways. Okay, so a lot of what I'm going to say involves concepts that were defined or touched on in the first talk today. In particular, cross modules were mentioned already. But instead of starting with extensions, I'll directly start with, we have two groups, and homomorphism between them and the action of the G0 and G1. And we have to have this action and the homomorphism playing nicely together, which is these two properties. And we have a category of cross modules, so we have these objects, these cross modules, which is this homomorphism between them. And then we can also say what homomorphism is between two such objects. And it's a fairly straightforward definition, this one. We just have, once again, homomorphisms here, as I said, the square communities, and one who's play nicely with the action. So, the most important invariants of cross modules are the pi0 and pi1, which are the kernel and co-kernel of this homomorphism. B delta, and we have that the kernel is central, and we have an action of pi0 and pi1, which gives us this exact sequence of groups. So, cross modules are of interest in topology because they are at two types. So that the classifier, so we can define a classifying space for cross modules, and which is a two type. So it has homotopy groups in degrees 1 and 2, and all other homotopy groups will be 0. So from this definition, the way I gave with two groups of homomorphism, where we have equivalence categories to categorical groups, as well as the integer groups, which are two types. So these are the idea is that in order to investigate cross modules, we investigate them because of their interest in topology, but we investigate them from tools from in the world of category. And in fact, this center will be a translation of things that exist in this world, which are then being translated into the setting and into the language of, which I just introduced, of having two groups and a homomorphism between them. And we are going to do this explicitly because once we have translated it into the setting, and again, I'm not going to be talking about this today, but the formulas that we will look at, which exist in the setting of cross modules groups, can then be directly or almost directly translated to the setting of the algebras, which is quite nice. Okay. So, as I said, we are going to be looking at things that exist in the categorical world, which is why I'm giving this talk here, I suppose. And so I'm going to talk about how we construct a category from cross modules. So, if we have a cross module, then we take the objects of the category to be the elements of G0, and the morphisms are going to be the semi-direct product G1 with G0. And so if you have, if you take an element in here, then we can say the source and the target in this way, as well as the entity. And we have position law as well. Given in this way. So this defines the term. Now, okay, so what do we want our center to be? So in the setting of groups, the center, among other things, is abelian. So if you take any group, its center will be a subgroup, which will be abelian. And so at the very least, we want our center, the way we define it here, to also have some sense of commutativity. Now, in the setting of categories, of course, we have, well, we have symmetric things, and then we have braided things. And unfortunately, we are going to end up with something that's braided. So, there exists braided categorical groups, and in the world of cross modules, these translate to something that initially is not a cross module at all. It's given as a homomorphism together with this bracket. But then it turns out that this bracket, with all of these properties, defines a cross module because we can define an action via this bracket of G0 on G1. So here X is in G0 and A is in G1. So, okay. So, and in the setting of the categorical setting, there exists something that people call the Drinfeld center, although I think this was independently discovered by Joel and Street. So, given a monadal category C, there exists a center which happens to be a braided monadal category. So it is the weaker form of a commutative. And so what is it? So we have for objects. So the objects of this category are going to be pairs, X and psi, where X is an object of C, and psi is a natural isomorphism, which kind of allows for some kind of commutativity. And then we also have morphisms, which are given via this diagram. Okay, so we still have to say the monodal structure, and then we have to say the braiding. So the monodal structure is given, so in the first component, we just use the monodal structure in C, and then the second component is given by this composite map. This is nice. It's nice to have slides because writing down these things would have taken forever. And we can also do the braiding explicitly, of course. Okay. So, and this is the definition that translated to the setting of cross modules, and so translated it in the language of groups and homomorphisms. So we have a cross module G, so we have a homomorphism from G1 to G0. Then we define a group Z0, which is a set of pairs where X is in G0 and psi is a map, just a map, it's not a homomorphism. G0, G1. But this third property tells us it's a cross homomorphism. So it obeys these three conditions, and this is a translation of what we saw before in the second groups. So, and the center is in fact going to be this cross modules, G1 to Z0. So Z0 will be defined as this group, which we just saw, and we can see that there exists a homomorphism, this delta, which makes this into a cross module. So we will also have an action of G0 and G1, of Z0 and G1. And so this will be a cross module, but perhaps more surprisingly, this vertical homomorphism is also a cross module. And this square here is a morphism of cross modules as defined at the very beginning. So this vertical. So first of all, we have to say what the structure is, and I'm going to do this explicitly because, as I said, the way this is now set up then translates quite nicely to setting of the algebras, which is work in progress, but should be the proof should be available soon for that one as well. The proofing for this one is already available. So we have the group structure is given by this, so it's quite straightforward. And we have the map from G1 to Z0, which again is, if you recall the definition of the center itself, it's this kind of similar. You see similar formulas altogether, so that they are quite, in some sense, natural definitions. And then again, the action is quite straightforward. It's just the first component acting, so it's the old action that we already had for the original cross module. And this is going to be a braided cross module, the center, which it should be, because we know that it should be from category theory. And the braid itself is defined. Again, it's very simple. We take the second component here and we plug in the first component. And this gives us a braided cross module structure on the center. Now, I also said that the vertical, I'm not going back, but so this vertical homomorphism is also a cross module. And in fact, we can think of it in some sense as the quotient. So when we have a center in the group setting, we have a group, we have its center, then we can consider the quotient of the group by its center. We can do something similar in this setting of the cross modules as well. So we had the center of the cross module, and now we also have something that acts like the quotient. So we have this vertical cross module, and it acts like the quotient in the following way. So if we look at the Hontoby groups, the pi zeros and pi 1s, the kernels and kernels, then we have an exact sequence where in fact we see the pi 0 and pi 1 of the quotient where we want them to be. Okay, and of course, as I said, this is a translation of the Drinfeld center, and so we have the following theorem. If we take a cross module and translate it into a category setting, and then consider its Drinfeld center, then this will be isomorphic to taking cross module, considering its center, and then translate it to a particular center. Okay, so. And now we want to kind of investigate the structure of the center, and we want to relate it to things that we know, and also we want to express this in terms of things we know from our cross module. So what we want is, well, for pi 1 we have what we want to see. Pi 1 of this cross module, so right here we have these two invariants pi 0 and pi 1, and somehow we want to investigate what they are going to be. And for pi 1 we have a straightforward result that can be computed by the group homology of pi 0 of the original cross module with coefficients of pi 1 of the original cross module. So we can see this is going to be nice and invariant and so on. For pi 0, things are not quite as straightforward. Pi 0 fits into an exact sequence. Here, where on the left we have H1 with so we have group homology, and the components here are pi 0 and pi 1, as well as here. However, the story does not stop here, and here we no longer have pi 0, pi 1, we just have G0. However, when G0 is free, then this gets split off, and life is good. And demanding that G0 be 0 is not that big of a restriction, because we can replace cross modules by a weakly equivalent cross module where G0 tilde is in fact the group. And in that case, then pi 0 fits into an exact sequence where everything is expressed via pi 0s and pi 1s and group. Okay, so which is going towards this idea of saying that this new definition of the center is homotopy invariant. So we can define. So we can say what is a homotopy between cross modules, and if we have cross modules where we insist that the G0 and H0 both be free, then and they are homotopic, then we have a morphism between their centers, which is a weak equivalence, which is what we would use. So this center is also related to non-real homology. So there's a relation to non-real homology, which there are similar concepts defined by different people. The definition that I'm using here is by Guillaume. It exists in dimensions 0 and 1. And H0 is defined like so. So this is a coefficients in a cross module. So it's homology with coefficients in a cross module. And so this is H0, and for H1 we first define derivations, and then we have the quotient of these derivations via this equivalence relation. And what we can see is that, well, the formulas were some pages away, but it turns out that they are similar, and so what we get this third homology is in fact this, or rather it's it's that. And then we also have the first homology is related to Z0. So derivations are not exactly Z0, but if we add one condition, so if we restrict. So for derivations here we had two conditions, whereas for the definition of Z0 we had three conditions. Some pages ago, I'm not going to go that far. So it's just missing one condition, so it's very closely related. And so there is this, we can write this in the diagram. So here is Z0 and here's the derivations, and we have this nice commutative diagram. So now I'm going to mention the other definition that already existed, which is Norris center. Norris center is a group, first and foremost. So for a cross module, no, so but so we have so what you end up with is this thing that so we have a trivial action here So this is the center of the trivial action, and we can consider this as a cross module where we think of the action to be trivial. And this is we can think of this as the and this is the definition of Norris center. So there exists a injective morphism of cross modules from Norris center into the center that I defined. And on pi1 we get an isomorphism, and there is a monomorphism on pi0, and in general this is not the weak equivalence. And I calculated a specific exercise. So probably the most common cross module is when you have a group and it's automorphism group, and you have right from G to O G, that's standard example of cross module. So and in this case I'm considering a small group before, and it's automorphism group. And for that particular case, I calculated both versions of the cross module of the center. And what you get is that so the center, according to my definition, would be this, where the first component is before and the second component is that group, C2 times before, and the homological groups here would be Z2 and Z2 squared, whereas Norris center is a much smaller object. In particular, it ends up just being, well, this is trivial, and this is not a weak equivalence. Okay, do I have any more time? I think not. So I will stop here.
Can also two types. So perhaps I have yes, this one.
Yes.
These initial groups always have only two vanishing
well,
groups. Can you explain how this works? Or is this
so when we start with, so that things get shifted up by 1 degree somehow. So when we are here and we are looking at cross modules, vectorial groups, we have the situation where we have simple groups of length 1. So we have that in the Moore normalization, everything is 0 starting from 2. And this grading kind of shifts everything up. So you get that k, so for k is 0, this normalization will be 0. And then from k greater than or equal to 3. So somehow everything will be shifted up by 1 degree.
would it be possible somehow to put the two models together to have a model for more complexes of length 2?
I mean, you could work on that, but I haven't done that.